Good morning. Good morning. Good morning. Okay. Good morning. Oh, wait, can you hear? Wait, I think you, yeah. Oh, and you cannot see me. Hold on. Good morning. Wait. Oh, I love it. All right. Good. Uh, Hold on. I'll put my good morning. Okay. Uh, so good morning, DJ. Good morning, Kayla. Oh, this is interesting because they don't. Oh, sorry. Okay. Good morning, Sydney. Good morning. Wait a minute. Oh, I should. Alice. Oh, funny how that works. Okay. Um, Good morning, chat. Um, where are the good morning? Wait a minute. All right, hold on. We got to the. Oh, I see the problem. Okay, wait. I want to make. There's going to be an announcement in the chat. Hang on one second. Okay. There's the. Good morning, Alice. Good morning, Tree. Good morning, Lena. Good morning, Erica. Good morning, Maya. Good morning, Sydney for the double. Good morning, Kayla for the double. Good morning, DJ for the double. Good morning, Sarah. Oh, oh, yes. Okay. Email. Sorry, I've been traveling more than usual lately. I am, if you've sent me an email, I mean, at least one person did, and I half responded, but yes, I apologize. I've been really behind on email this weekend, but yes, I hear you. And in fact, let me, just in case, let me remind you all right now. Hold on, I'm writing this in the chat. Yes, I normally I pride myself on being really fast with email, but like lately that is definitely I have not been. So there's at least one person in particular I'm talking to. And good morning, Loani. There's at least one person I'm talking to, but any of you, if you do send me an email and you don't hear from me like within a day, really, please send me a text and tell me who you are. Oh, and that's Haley. I love it. Okay, hold on. That's so cool. Okay. Oh, and also I don't mean to be, hold on, we're gonna switch to view, obviously. Um, um, as I said, I have been traveling on some of that. Okay. There's also an announcement in the chat, but if you just came, you won't see it. Hold on, let me put it again. The Whoa, how did I didn't mean to kill Sydney, to disappear Sydney. Okay, the announcement in the chat is a reminder of something that's already in Google Classroom. I don't mean to make a big thing right now or to get too rabbit hole about it, but just to remind you that we do have an exam in 2 weeks, which means an exam that's due in 2 weeks. It's a take home. It's like one humongous homework with higher stakes than homework and where it has to be on time and can't do infinite drafts and stuff like that. But it's like the homework. It'll be posted a week from this coming Thursday night, and then you do it at home under non-testing conditions, and then you turn it in by Tuesday morning of March 17th. Um, a practice version, an old version, well, a recent version of such a thing is already in Google Classroom, but I may update that to make it more accurate or more of an accurate representation of what you're going to do. Um, we'll talk about it more. The practice document in Google Classroom is for practice. It's just for your sake. You don't turn it in or anything. Wait, I'm going to just do this chat announcement again. So this announcement in the chat is just a logistical reminder of what it already says in Google Classroom that you will have an exam in 2 weeks, and it is take home, and that means it will be posted like 5 days prior to that. And I will address, as we get closer, I will address more questions about it. The best way you could ask in class, the best way you can ask me questions about it in class is to look at the practice document in the Google Classroom and start trying to do it and see how you feel about it. Some of the material in there we still have to get to before the exam. So again, I'll say more and more about it as we get a little bit closer. But I just logistically want you to be aware. Oh gosh, what just happened? Oh yeah. I think I just did I just remove one of you? I did not mean to do that. If I just kicked you out. Okay. Um, but the best way to prepare for that exam really is to keep on doing the homework and keep on revising any old homework until you see how to satisfy the rubric to get all the points that you can, because the exam will be the same kind of structure with a rubric and everything. With the rubric available in advance, once the exam is posted, before you start doing the exam, the rubric will be there. So, and five-step method and all that. So it's just like one big homework that you do in the same conditions that you do homework. So, just keep trying to get more and more used to what the expectations are of these homework documents, because they're all in service of practicing exam. All right, so that's just a logistical announcement. We'll talk more about that um, as we get closer. What I want to do now is get back. I want to get back to the material. We've said enough about vectors for right now. I mean, we said a lot about vectors last week. You will need that stuff about vectors later on, and some of it might have helped you maybe revise whatever you did in homework number 2. But right now, I want to get back to other aspects of homework 2, the differential equations and stuff that you really need for the material that you're doing right now, specifically this, exam material, and also by right now, I mean lab. So while so what we're going to start doing here is going to go back. Well, here, I'll post. I want to go back to this document. Let me screen share. We're going to go back to this document is what I want to be going over sort of explicitly. We're not going to go over every single problem in this document, but we're going to go over some, and particularly the ones that we're going to go over in particular, like lead to ideas that we're really using right now. So you can see the document, right? So I feel like exercise A and B we've in effect gone over in class several times. I'll emphasize again, I am looking for diagrams in these homeworks, no matter whether I give you a diagram or not. You do need to put a diagram. I think I said this last week, so I don't want to get rabbit hole, although you can stop me if this is totally new information. Like, I am expecting step 1, step 2, step 3, step 4, etc. Step 1 does include a diagram. Actually, yeah. I'll do it. Well, I'll just say the diagram that I'm expecting would be a cosine graph. One axis would be labeled T. That's how we would know what we mean by T from then on in the computations of the problem. One axis would be labeled X. So that's what we would know and T is measured in seconds and X is measured in meters. That's how we would know what X and T mean for the rest of problem A, let's say. Then the y-intercept of that graph, where the cosine starts, would not just be the number 1. It's not just it's not just a abstract mathematical cosine graph. It's specifically the cosine graph x equals a cosine omega t. So the y-intercept of that graph would be capital letter A. That's what cosine equals when t equals 0 for that graph. So you would label A, and that's how we would know from then on what A means in your math. We mean the initial and therefore maximum value that this oscillation ever obtains. And then in that graph, between two peaks, you would label the interval between the two peaks or two troughs or anything in that graph. You would label that capital T, the period, like the duration of one full cycle of that graph is capital T, the period. And you write off to the side that 2 pi over capital T equals omega. That's what is meant by omega for the rest of the math, right? In other words, the purpose of the diagram, the purpose of any diagram would be that every label in the graph serves as a definition for that term in the rest of the computations we're about to present. Again, this is part of the 5-step method, but it's also part of what we larger mean by a self-sufficient document. You're continually giving the reader everything they need to follow the rest of the document. The document is a guide to itself. That's what I mean by self-sufficient. I mean, that's part of what I mean. I might even say on a side note, it's good to have a title on the document. The title could be Physics 204, Homework 2, Math Methods, whatever. But like, just keep thinking of every document you turn in as something that should be able to stand on its own and bring a reader in and provide the reader with all the tools that they need to follow the reasoning of the document. And then the document has tons of reasoning that brings you from a starting point to a conclusion. I'm overemphasizing this as usual because that's what you're trying. All of this is practice for an exam. That's what we're looking for on the exam. So you would do a cosine graph with all those labels on it, and then you would proceed through to do step 2. What is the question? You take in step 3. I think we've said this before, so I'm trying not to write this down. I want to get you would then take derivative. You would present in step 3 the chain rule, and you would present that also in general, there's a thing called the chain rule in math, and also in general in math, there's an idea that if you have a cosine function, the derivative of it is negative sine. You'd present that in your best possible, most clear way in step 3. Then in step 4, you'd put those things together and take a derivative of a cosine omega t. And finally, in step 5, you would put your final answer circled. And what would your final answer be? It would really be if x equals a cosine omega t, then dx dt equals negative omega a sine omega t. Like, your answer is a statement that stands on its own. Your final answer circle is not just negative a omega cosine omega t. Like, that's not an answer. That's a fragment. That's half of an equation. That's just like an idea. I am being critical, I guess. Your answer is that dx dt equals blah, blah, blah. Like, that's a full statement now. But dx dt of what? When? Who? What dx dt? If x equals blah, then dx dt equals blah. That's your final answer. You circle it. Okay, so that's the kind of thing I'm looking for. And then you do the same thing for exercise 2. And then the answer to B, I'm doing this fast because I'm trying to get to a certain exercise to actually teach something that we need this week. So stop me if I'm looking at I can't see. I'm looking at 85 screens at once too. So stop. I don't think there's anything in the chat. So I'm just sort of blasting through. Then in question B, is x equals a solution? Why or not? Yes, it's a solution. You show that by switching the order of omega and a. You'll see that you have that when you take two derivatives, you have d2x dt squared equals negative omega squared a cosine omega t. And that whole a cosine omega t thing, that whole thing is x, is the x that we assumed. So therefore, yes, the second derivative equals negative omega squared times the original function. So yes. So what all that means is that is a harmonic oscillator. Okay, so then you go to exercise C. You do all the same stuff for exercise C. You keep saying C above. Like, you don't have to draw the diagram again. You don't have to explain chain rule again. You've done it once. So now you just say, like, but you do acknowledge all the steps. You say, like, step 1, C above. Or for diagram, C above, whatever. Step 3, for the general principle of chain rule, C above. And if you do all that for exercise C, I'm on now, exercise C, you find it's not a solution because at the end of the day, five is, sorry, at the end of the day, the square root of three is not five. I mean, that's why I'll kind of leave it at that. But like everything works except for the three and the five don't match up. So it's not a solution. What does that mean in English? I'm looking at exercise C now, and I will change a lot in a second. I'm looking at exercise C. When I say that is not a solution to that, it means that d2x dt squared equals negative 3x does describe a simple harmonic oscillator. Like that differential equation is a simple harmonic oscillator. And a cosine 5t is a simple harmonic oscillator, but they're not the same simple harmonic oscillator. I don't know if that makes sense. Oh, chat. So I'll say that sentence in the chat. Like I'm saying, one describes a simple harmonic oscillator with an omega of 5, one that's going 5 radians per second. The other describes, so back and forth at that rate. The other is describing a simple harmonic oscillator that's going back and forth and back and forth at the square root of 3 radians per second, the square root of 3 radians. So they might both be a mass on a spring, but it's either different values of mass or different values of K. They're going back and forth at different rates. I'm looking at exercise C right now. I'm going to pause because there's at least one thing in the chat. Also, I know the view on the screen is like not helpful to anybody. Hold on a second. But no problem. No problem. Got you, chat. Also, though, I'm going to pause for a second because I know I'm rabbit hole. I'm just going to, there's something in the chat that most of you have seen, but if you just joined recently, I don't think the chat would show you this. So hold on one second. Okay, so the announcement in the chat is about the exam. I don't want to talk about it right now. I don't want to get, but it's a reminder of logistics, and all that information that's in the chat right now is also in Google Classroom. So, and you can reach out and ask me about, we'll talk about it more later. I'm not just going to drop it on you. It won't be a surprise, and also I'll put this in the chat again also, and then I'm going to switch it. All right. So, okay. So stop me if there's other questions. Ooh. So here, if I'm sort of making sense, I hope, then I want to move, and I'm going to start working this out. Believe me, I'm going to start working this on the board, but I want to skip. Okay. So I just overviewed exercise A, exercise B, exercise C. Oh, D, it's funny. D is sort of going out of order. D is just like the explanation in a way for C. I mean, honestly, in order for you to do C properly, to get the answer no that I just said for C, you have to go through the steps that it's asking you in D. It's kind of out of order. It's sort of just asking you to justify your answer above. And if you did it properly, even for D, you could literally say C above, if to part C. E is the same thing over again, right? What we're emphasizing there, or trying to remind you, E is bringing us back to the basics that led us to all of this in the first place. It's already presenting omega as K over M. Like if you're starting to get confused or like, wait, I don't know when to use omega or when to use K over M or whatever. K over M means specifically, truly, we have actually a like mass on literally a metal coil of stiffness K. This all came from that assumption. But what we're trying to say over and over again is now that we know how a mass on a K works, how a mass on a spring works, we're now believing that the math that we've figured out for that would then apply to anything that starts with the same math statement, with the same type of differential equation. So it's not K over M once it's a pendulum on a string. Then it's like G over L or something. And it's not K over M when it's an electrical field, which we'll get to later. Or then it's some other parameters. But so K over M is very specifically mass on a piece of metal. Anything else that's a harmonic oscillator acts like a mass on a piece of metal, but they have different parameters. I don't know. So what covers all the cases is calling them omega. I don't know if that helps or not, but so E is the same thing again. It's all the kind of exercises. But now it's F. I want you to look at F for a second because that's I'm going to switch the boards now and the view and like start taking notes with you and solving F because F is another exercise of a very similar type, but F actually then shows us something that is unexpected perhaps and that we need for life and for the lab and for the rest of the material. So I'm going to switch the view. So we're going to do F now. Uh, is that yeah, okay. So we're going to do F now. Uh, how do we do this? I forget how to do it. Where to go? Oh, yeah. Okay. Okay. Um, okay. Okay. So we're going to do this now. The thing that's written on the board right now is my ultimate goal, or my goal in the next like 25 minutes. Okay. The thing that's written on the board right now, I don't think you already know. I think it's what I'm about to show you. Um, okay. Okay. I should have written it first, but here's my I'm looking at the chat. Okay, here's my step one. So I'm doing F, right? Here's my step one is a cosine graph, like I said before, with T labeled, with X labeled, with A labeled. Everything that I'm going to use in the math is appearing as a definition, as a label in this graph. And it's a cosine graph, just like before. But now whether you figure this out in your head, whether you know this from a prior math class or you try a graphing calculator or Desmos or something to figure this out, you'll notice that because there's like this number stuck into the parentheses now, like that's the new thing is that there's a number stuck into the parentheses. The whole cosine graph is shifted over, um, I think, to the left by some amount. Now that amount seems to be saying 3.5. Um, That is an arbitrary that on the one hand, that's a constant. That is a number, 3.5. It's not a variable. So whatever it is, it's not going to change throughout the problem. So it's functioning, I mean, excuse me, it's behaving as a constant. On the other hand, it's an arbitrary constant. Like, I don't know if it's evident or not, but there's not, we're not intending to convey anything special about the number 3.5. In fact, that's like not even divisible by pi or anything. It's just a number that's supposed to ask us to start thinking about what happens if there's an extra non-zero number thrown into the parentheses, right? That's the question here is like, what effect is that going to have like on our life? So step one was the diagram. Step two, like, what is the question? Okay. The question is, what is the derivative of this function, right? Step three, what are general definitions and principles? Well, these would be, again, the same principles as you would have done above in the homework. So I'm going to say, see above, I'm assuming above you have some sort of presentation of the chain rule and of whatever trig derivatives we're using to do this. And you would present them. You would take a beat at the beginning of the document to actually explain what they are. Um, and I can't resist saying this. If sometimes step three is like really where the action is in a way, it's like really where the physics thinking. It's the hard part. Step three is like where you have to think about what you have to think about in order to do the problem, and you have to make a decision about how much to break it down. Like how much are you really supposed to explain things that we're supposedly already knowing before the problem even began, right? And let me say that again for the sake of this, or if you're trying to get more points revising your homeworks or trying to get used to this approach or you're trying to prepare for the exam, step three is where you write down things that we supposedly have already established to like in physics and are now going to use for this situation. That's what step three is supposed to be. You have to make some hard decisions often in step three. But then if the question is how much am I supposed to explain something that we supposedly already know in physics in order to do this, the answer is a lot. If it's the first time the idea is coming up in a document, err on the side of more explanation rather than less. Kind of like in the sample document that I, posted in Google Classroom. Again, I'm going to make another one that's like more in handwriting and colors and stuff. That's more like the style of many of us. But it doesn't, but it's not, but whatever your style is, the idea that's a physics idea that you're going to use or a math idea that you're going to use for a problem, you want to over explain. So anytime in your brain it goes, wait, now I'm going to divide, like whatever you want to over explain. Okay, but I've already done it earlier in the document here. So, and that's part of why you over explain it. You're not going to do it a million times. You're saying everything you need to say so that you don't have to say it again. All right, so I've done that here. So now to get to the meat of this. So step four, like I'm going to actually, take this derivative twice. Sorry, someone's here. Sorry. Okay, so now step four to cut to the chase. Well, the function was this, right? So I got to do chain rule. So I have to take the derivative of the whole thing times the derivative of what's inside, right? If I'm being really explicit, let's say I call this inside piece, let's say I call that U, you call it whatever. Then actually, I'm going to ask you guys, I'm going to pause for a second for direct chat here. It's not a trick question. It might be tricky, but it's not a trick. I want to know if my inside used to be like omega t in the older functions. In this one, it's omega t plus 3.5. In the direct chat, if u equals omega t plus 3.5, if the inner function is omega t plus 3.5, what I want to know in direct chat, please, I'll wait till I get like three people at least. What I want to know is what is du dt? Like, what's the derivative of the inner function? I'm asking in direct chat. I'm going to ask right now. What is du dt? The derivative with respect to t um, of the inner function. I just got an answer. I'm very proud. Oh, I think the direct chat would be better, please. I think. Hold on. But the person who just went in the public chat, I'm going to say I'm very proud and happy that the person did just go into the chat, and that person should. I don't know why I'm being a tree. Should definitely get points. Um, but I'm literally not going to say whether I agree or disagree with that person because I'd like to hear other people too. Okay, whether that person, whether tree is right or wrong. First of all, he's getting points either way. He'll get even more points if he's wrong. Weirdly. But yeah, okay. So I'm seeing other things in the chat now. Great, great. Okay. And I'm seeing and try to keep it to and same thing with Fabricio. Like, thank you very much. This is awesome. And it is helpful that you're in the public. Like, it's not anyway. I'm just saying you don't really have to be in the public, but okay, great, 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 great. I'm seeing a lot now. I'm seeing a lot. Awesome. And I'm going to say that almost every answer I'm seeing is different, which definitely tells me that we're not wasting each other's time. Like, we do need to work this out, I think. So I'm going to wait a little longer. Great. I'm seeing like seven answers in the direct chat. That's great. I'm going to read them out in a minute, not the names, but just to show you how much variety there is here. But I also want to repeat the question. So this is calculus. And to address, the concerns of this class from last week. I mean, so this is like calculus, right? And I will admit, I'm about to show you something new. I'm doing this exercise because I want us to see something new in physics. I'll admit, to be objective, this piece of calculus we're doing right now, like in principle, you know it from a previous semester of a math class. Like in principle, you come into this room sort of at least having seen this before. That doesn't mean you've but so I think that does mean if this kind of stuff is, I'm going to try to explain the answer in a second, but if this kind of stuff is giving you like a lot of stress, I hope you do reach out to me personally. We talk about it and we can look at like your old notes from another class together or, whatever. We can break this down, but this is not meant to be new. But okay, so I'm gonna. Okay, good. Now I'm getting some actual questions in the chat. So someone's asking in chat. Wait, hold on. They say, are we applying chain rule to the inside? Right. So what I'm doing is So let me back up for a second. I will tell you the answer, but we're looking at this whole. We're trying to get the derivative of this whole function, a cosine omega t plus 3.5, and I am believing that in order to get the derivative of the whole thing, we need to use the chain rule. Like, we need to take the derivative of the outer and multiply it by the derivative of the inner. In fact, let me back up one more. So yes, we are using the chain rule. But to be really clear and really maybe technical, I think I am right now just looking at the inside and trying to take a derivative of the inside. Like, in order to do, like, I'm not, so technically, what I want to say to everybody is it's not that I'm applying the chain rule to the inside. I'm just applying a regular derivative to the inside so that I can separate that derivative in my mind from the derivative of the outside and put them together in what we call the chain rule. Like, so I'm going to slow this down a second because I am getting a lot of different answers in the chat. So I think there is like something going on here. Um, I'm saying, so let me back up. Like, okay. Okay, this thing that I just I'm taking a step back and I'm writing out the step three that I might have written some earlier exercise to be clear. Here's what I think the chain rule is. The chain rule is if you have some function, u is a function of t, let's say, and x is a function of u, right? So you got a box that you put a number in and another number comes out. But that number that comes out now goes into a new box and spits out a new number. If you have a function of a function, I'm being in general now. I could have written these about with y's and x's, but I don't want to confuse you any further. So I'm saying, like, if you got a u rule that spits something out, but then you apply an x rule to, oh, in fact, sorry, to the thing that got spit out. I guess I should use two different letters here. Sorry. Okay, then the derivative of the whole thing equals the derivative of the outside times the derivative of the inside. Because if you write it out this way, that makes sense. Like derivatives are fractions, they are ratios. I mean, so my answer to the person in the direct chat is, are we applying the chain rule to the inside? Well, we are applying the chain rule, and I am looking at the inside. But really what I'm trying to say is the chain rule says, look at the inside and just do a regular derivative. The chain rule says, multiply the derivative of the outside times the derivative of the inside to get the derivative of the whole thing, which I'm going to right now do to tell you the answer. But please notice, because I didn't want to get on this soapbox. I mean, this is a place where people like lost points in homework, and I'm pretty confident you may not understand why you lost the points. Is notice nowhere in this explanation of the chain rule, I don't have any kind of primes going on at all. There's no f prime or g prime. There's a way to use primes that's correct. There is a way to use prime to mean derivative and to be correct about it. But honestly, I think it's a much more confusing notation. When we're in a physics class, it's much less clarifying to use the prime notation. And especially if you take the prime notation from one place on the internet, if you take something that sort of looks like it makes sense on the internet with the prime notation, but then you sort of accidentally morph it into something that has dx dt or dy dx or something like that, they actually confuse each other and start saying things that don't make sense. What I'm trying to caution you is don't use the prime notation. I'm not saying it's always wrong, but it gets in the way and it makes life harder. I'm saying always think of a derivative as a slope. A derivative is a slope, just a slope of a tangent line, a slope taken to the limit. So instead of saying delta y over delta x, like normal everyday slope, we say d over d, meaning it's really, really infinitesimally small. But the derivative dx dt equals the outer times the inner. So in this case, to get back, so in this case, so here the function is, so here, like u stands for omega t plus 3.5. That's u of t. Let me be more clear. The u of t is omega t plus 3.5. The function that we're doing to t is we're multiplying it by omega and then we're adding 3.5 to it. And then x of u is a cosine of that, of the thing we did above. This is the chain rule. We're thinking of the one big function as a composite function of an outer thing that you're doing to an inner thing. So then, to answer the direct chat person's question, so I'm going piece by piece. So I'm looking in the inner, in the u function, u of t is omega t plus 3.5. So I'm literally asking, what is the derivative of that with respect to t? And really, I'm not going to shut up now. I'm going to go back to the chat now, but I want to give you sort of another chance maybe to correct your answers in the chat, some of you. I'm saying, and I'm saying now, if you just pretend you're in a math class. You're walking into the math class, and on the board is just this function, omega t plus 3.5. In fact, I could really, like, is just literally what it would be like this. This function that I'm looking at right now would look like this. Like literally, you have a straight line. Like if you just focus your attention on this as though it's its own function, the independent variable is t, the dependent variable is u. The function is apparently a straight line. It's like y equals mx plus b. Only it's only it's u equals omega t plus 3.5. Yes, absolutely. So I'm saying that inner piece, you might even want me to, somebody might even want me to go back 2 slides actually to make this point. I'm not sure, but the inner piece is its own thing. And what it is a straight line with slope omega and y-intercept. Oh, no problem. Thank you. And then please apply for points for that. That's like totally counts for helpful participation. So I'm going to go back, right? I know I'm like sputtering, but I'm excited. I'm not mad at all. I'm excited. I feel like you're giving me something to work with, all of you, okay? The people that gave me right answers and the people that gave me wrong answers and the people that are asking me questions. I feel hopefully like at least 7 of you are with me right now. And I think there is something to be straightened out here. And like, I think there is, and look, I'll be really honest, because I saw, well, it was in your section. I feel like I've seen in one homework like a lot of like little explanations of the chain rule, certainly across the board this semester I have. And a lot of them have a lot of F primes and G primes in them that are, coming from the web and are fine. I'm not saying anybody cheated and I'm not saying anybody did anything unethical, but I am saying I think I could tell from the F primes and the G primes that people are writing things down that they've remembered as the chain rule, but they don't necessarily really understand what they're writing down. And what I'm trying to say right now, and that question, I just want to emphasize again, and I really want you to submit for points. When the person asked in the chat, wait, are we applying chain rule to the sorry, they wrote, the exact words that someone wrote were, wait, are we applying chain rule to the inside? That is a perfect question because I really shows exactly where people's mind, at least one person's mind is on this. My answer is we are applying chain rule. But to apply the chain rule means that we look at the inside as though it's its own thing. Like we're breaking this down into pieces where each piece doesn't need a new rule to understand. The rule is how we put the old pieces together. And that really honestly might be part of what's confusing a lot of people. So I'm saying this function is so again, I'm just yelling because I'm excited because there's like something for me to say, not because I'm mad or whatever. Uh, so the function is x equals a cosine omega t plus 3.5. I mean, like, right? This is our function right here. So what we're doing is we're zooming in all the way to the parentheses and saying, that thing in the parentheses, that itself is a little function. Call it u. That little thing is u equals omega t plus 3.5. So then, and by the way, I am not just talking to that one person because remember, I've seen all the answers in the chat. So I know there's a confusion going on here. You'll see in a second. I'm saying if we now zoom into that parenthesis in the chat, that u equals omega t plus 3.5, okay, that's its own thing. That means that we've got inside the parentheses a straight line whose slope is omega, whose y-intercept is 3.5, and I want to know the derivative of that. So listen, the answers in the chat right now, well, in all the chat, one answer is omega t, one answer is omega, one answer is t, another answer is t, another answer is either omega or omega t equals du dt. Another answer is omega. Another answer is omega. So that's a lot of different answers. So I'm going to pause for one more. Now that I've like yelled and yelled and yelled, I'm going to pause. And remember again, you get points if you get a wrong answer. So don't, but just try. Anybody, certainly I invite anybody who hasn't said anything, please say something in the chat, even if it is, I kind of understand what you're talking about, but I do not feel like I can give an answer right now, or like whatever. Give me something in the chat, even if you have not said anything at all. And if you have said something, like say I stand by my answer, or now I'm not so sure about my answer, or some, or nothing else. Let's make this a new thing in our class. If you can't say anything at all, like if you don't feel like saying anything mathematical, just give me a rating scale from 1 to 5, not of me as a person, but just give me a rating scale of how much you feel like you know what's going on right now. Like 5 is like, I totally know what's going on. I don't feel like giving you an answer. And 1 is like, no, I mean, I'm like, I could not be more lost. Okay, just something. Like, thank you. Okay, people are doing it. Thank you. Okay, thank you. I see. And I will read the numbers in a second. Maybe I'll make a new portal for whenever people participate in this. Okay, okay, okay. I see. No, this is helpful. Okay, okay. I see like 4. All right. Oh, okay. Hold on. Okay. You know what part of the thing might be in this class that we need to work on, that I need to work on, is what the very thing that makes me very happy probably makes you unhappy, which is that there's a huge variety in this class. Like literally, even on the question I just asked about like where are you with your comfort level, literally I got a 3, a 1 to 2, a solid 2, a 5, a 4, a 1 to 2. Like that's a huge variety. On the one hand, that means to me, that's exciting because it means there's something happening. Like, no wonder we have confusion because there's different, but to you, that's probably frustrating because people need different things. Um, okay. But I'm hearing you. I mean, I see why there's an issue, sometimes. So I think the best thing I could do right now, one thing I am committing, the other thing I'm going to do, folks, because definitely part of this is online. I mean, we're all trying as hard. Clearly, you're trying hard, and so am I. I mean, we're trying to engage, but I could tell from the other section that's half online and half not. The minute we get together in person, it's like always easier to break through these barriers. So one thing I am going to do is make a point of visiting you somehow in your lab on wait, you have lab on Thursdays. I'm not usually in the building on Thursdays, but I don't know when I can do this, but I will make a point of visiting just so that we can all like have a little more something. But for the moment, what am I going to do? I think I'm just going to say the answer. If you have any advice in the chat, you want to say what I need right now is blah, please feel free. But in the but in the absence of that, I'm going to tell you. Or does anyone want to change their answer at all, or no? Well, all right, I'm going to tell you what I think the answer is and see if you can do anything with it. I think the answer, and many people said it, but a lot of people said something. Well, I'm going to stall one more second. With all due respect, the answer. Well, no, I'm just going to say the answer. The answer is this. The answer to the inner function. The answer to the inner function is omega. The derivative of the inner function, the derivative of this is just omega. If you looked at that, that's like, literally like saying, here's a function, y equals mx plus b. What is dy dx? If y equals, I should have asked this in the chat. If y equals mx plus b, what is dy dx? In other words, what's the derivative of y equals mx plus b? In other words, what's the slope of a straight line mx plus b whose slope is never changing as m? The answer is m. That's what this is saying. I don't know if that helps at all, but the slope of this inner function is omega. Therefore, okay, and back to the problem now. So back to the problem. Like we said x. Well, yeah, we said x equals a cosine omega t plus 3.5. We want to know dx dt. So what we're saying by chain rule is dx dt equals dx du times du dt. That's literally a way of saying the outer derivative times the inner. Um, um, uh, we said that u equals omega t plus 3.5 and x equals a cosine of u. So dx dt equals negative a sine of u times du dt. Like I'm saying, this is what I mean by the derivative of the derivative of the whole outer package is negative sine, but the derivative of the inner we just established was omega. So the answer to the whole thing, oops, well, yeah. So the answer to the whole thing, like if you want to do it like this, so the derivative of the outer is negative a sine of bleh, but then the derivative of the inner was omega. So we take the derivative of the outer and we multiply it by the derivative of the inner. Again, the chain is the idea that we're putting those two together, multiplying them. But each piece we just do by old derivative rules. So I can clean that up a little bit and say the answer to this first derivative is like I'm saying like three things right now. Number one, I think this is the answer. Number two, I think this is the way you should write the answer. And you could write it back. I wrote blah if blah. You could write the other way around. Blah, whatever. You could say if blah then blah, whatever. But I'm saying if x equals a cosine omega t plus 3.5, then the derivative of that whole package, where we're treating x as the dependent variable and t as the independent variable, the derivative of the whole package is negative omega times a times sine of omega t plus 3.5. First of all, that's what I'm saying. Second of all, if we back, well, wait, let me look at the time. Tell me honestly, is there put in the direct chat either please say even I know look, I know you're not like perfectly clear with it. You couldn't be just from one example, and I wouldn't expect you to be, and neither should you. But put in the direct chat if either you're slightly more clear on this than you were 5 minutes ago, or if you have any kind of question that can help yourself. Okay, okay, good. There's a question. That was the other option. Wait, for the last example, when we do derivatives, omega would just be a coefficient. Yes. Cool, cool. Or first of all, someone's saying I understand now five. That's great. Okay. Second of all, someone just wrote in the chat. I'm wondering if it's the same person who wrote that other hole. I'm just, oh no, this is a different person. It's great. You see, you guys are actually a really good, you are getting your money. You are good students, real honestly, because someone else who's totally different, and in fact, who said that their understanding was not that high, just wrote, wait, for the last example, when we do derivatives, omega would just be a coefficient when there is an omega t, like question mark? Yes, that is the point. Yes, that's what I'm saying. That omega, we are treating like it is just a coefficient. You are 100% right. And how do we know that? Because it's a constant number that is directly before the variable. Like, I want to dwell on that for a second. Great question. You should definitely submit for points. And if that's the question that's in your mind, the answer is yes. You get, if that's your litmus test of whether you just something just clicked or not for you, yes, something just clicked for you, I think. Like, yes, you are correct. It is a omega we are treating as a coefficient. Omega, in fact, is a coefficient. In fact, and that's also what we've been doing the whole time. Even last week, even the somewhat easier examples, we've been doing this chain rule thing, whether we knew it or not. And we've been looking inside the function and saying inside that cosine, we just have like a little straight line where the coefficient is omega. And I'm going to shut up in a second. I'm going to go back to the chat, but I'm a little bit excited. I feel like someone just figured something out for themselves. Um, and I think a larger lesson here is part of what is hard about all of this. Part of why even some of you are like, I've even done this before. I even took calculus at another college or whatever, at a harder college, and I got an A. So I knew it. So why is this all of a sudden so like what? Like you might be mad, some of you. And part of the reason is it looks different now because all the letters are different. I mean, I'm honestly, and it's when we get used, part of it, we get really used to like Y's and X's, and we think we have a bunch of rules in our mind about how Y's and X's work. And we don't quite realize how to transfer those rules when all of a sudden it becomes X's and T's or something, especially if X used to be an independent variable. And now in physics, it's often a dependent variable. That may be throwing a lot of you off. What I'm here to say, and there's very few numbers now, like the 3.5 just like came into our life today, but like a lot of this is a whole bunch of letters. And the first thing to really try to get straight at any moment is like some of these letters are functioning as independent variables, some are dependent variables, some are constants of one kind, some are constants of another kind, like configuration versus parameters versus some are constants like constant coefficients, like the person just said in chat. The real, and there's very few numbers. So they all look like letters, but they're treated very differently. And part of the thing to get used to is which one is which at any given moment. Absolutely. I'm going to go on. I'm looking at the chat. But I'll look in the chat. All right, you understand it now. Great. Made clear now. Great. I'm glad. And you. Oh. Oh no, right. Sorry. No, most people are in the private chat, and that's fine. The message that I just read out loud. I'm going to read it again just really quick. Is private. It's not public, but I'm reading it out loud because I'm not saying the person's name. Okay, that's my deal with you guys. I want you to use it if you're more comfortable using the private chat because you don't want other people to know what you're thinking. I'm good with that. Like I think some people are more comfortable with that. But if it's like about math or physics, I'm going to read the content out loud sometimes because I think it's so helpful to everybody. So yeah, no, the thing that I just read was not in the public, and that's okay as long as you all understand. I won't give your identity away if you go private, but I certainly might discuss the content because I think it's so good and helpful to people. Okay, wait. Oh, yes. And then someone else just said, okay, I understand how you're getting the answer, but I still need some practice. Right. Well, that's also why, yeah, we all need practice for all of this stuff. And I know you need to know that I know that. Nobody ever gets this stuff just the first time. That's also why the math homework is so long because it's a lot of practice. But that's also why you can still redo it for practice to get more points. Like the opportunity is not, as you like go back and practice these more. Absolutely. Okay, wait. Okay, so here's another question in the chat. Wait, so in the omega t, when you do the derivative to take an omega out, oh, okay, see, here's kind of like the same type of, wait, so in the omega t, this again is private. And I hope you understand. I'm reading it out loud because it's a great question. I'm just not saying who's saying it. Wait, so in the omega t, when you do the derivative to take an omega out as a do you take the omega out as a coefficient because it is a constant? Question mark. Yes. Yes. That is the point. And please notice, please, everybody, I hope you don't think I'm upset. I'm like so excited. Like two people in the direct chat just kind of asked the very similar question, and I just kind of said it twice. That's a good thing, not a bad thing. I'm very convinced that they wouldn't have asked that if it were in the public chat, honestly. And I believe that at least two people in the room think they're the only one that was having that issue or whatever. But it clearly, at least more than one person just realized, Yes, we're treating the omega as a coefficient because even though it's a letter, not a number, it's a constant. It's a letter that stands for a constant. It's not a variable. So it is just a number from a physicist's point of view and from a mathematician's point of view. It is just a number. It's just a number that could vary from one lab group to the next. Like, I mean, within a lab group, it's just a number. Like, seriously. Omega, that's the point of all these graphs and these diagrams that you do. Just like capital A is just a number. It's just a number. It's just a number. We're not specifying what it is. It just might be one number on one day and another number on another day. We're trying to be general and learn these relations. But yes, the really big thing is like, what is a constant and what is a variable? The variable in this situation, the independent variable is t. T to us is like the way you all in a math class used to treat x, but we're treating t because everything is happening as a function of time. So t is the variable, and then x is a variable as well. X is the position of the oscillator. Those are the variables. One is independent, the other is dependent. Like one is this axis and the other is that axis. Everything else that looks like a variable isn't a variable. It's a constant. And that is a revelation, I think. I bet you it's not just for two people. So it's great. Okay. And then someone said, understand it's a solid 3.5 then. Okay. Okay, yes. So that's a big thank you. So you're helping me help you guys. Yeah, the point is that omega is a constant. Absolutely. Same with A. Okay, and now what I'm going to say, and I will move on, but I'm also going to say to all of you, this is great. And honestly, like I know I talk a lot. I know I take a long time to get to the point. But I'm hoping you guys are seeing that part of that is like I'm trying like at any given moment right now, some of you are bored to tears. Some of you are probably not in the room, obviously. Some of you are going to feed the cat because like you already get it or whatever. Okay, fine. But just know that this is not off the topic, right? This isn't us like getting distracted. This is us spending time on the people that like are actually having an educational moment right now. So if you're feeding the cat, that is fine. Just know that it'll be your turn next time. Right? Like we're not off the topic here. This is the topic. And I'll leave it at that. But I hope you are like, I'm very willing to do this if you guys are. And believe me, I've been doing this long enough that if spending this amount of time to actually get the fundamentals of the calculus straight, I know that means you'll be able to do other stuff faster once we get this straight. And I know what steps I can skip later on in the semester so that we still get to all the material or blah, blah, blah. Don't think that this is slowing you down in the course. It is not. It is speeding you up in the course. Ultimately, you're setting up your shots better now. The shots will be better. You'll sink more balls, like so to speak. But really, I want you to know that. So if you can do this with me of breaking things down and show me where I need to break things down for you, we will get to everything, even if it's like in our own way. Okay. So I'm glad that we're doing this. I'm going to move back to the problem now. I am watching the time. I want to ask you one question too, though. Speaking of the pace of the course and all that, in the private chat, can you remind me, please? Did you wait? Today's Tuesday. You have lab Thursday. Last Thursday, can you just remind me in the private chat? Did you start lab 3 last, or where are you in the lab? Like, did you start lab 3 last Thursday, or did you board meeting? You had a board meeting. Okay, good. And it was a board meeting about finishing up lab 2, or it was about whatever it was. We did a board meeting. Okay, which actually sounds very appropriate. Okay, great, fine. So that means we're starting lab 3 this Thursday. Perfect. So that means, okay, good. So I'm going to go back to this and I'm going to get to something that will start helping you for lab 3, but I'll really turn it into a thing that really lands a ship in Thursday morning's class. So long way of saying, so it's 10:29. I'm going to get back to this thing now. The goal here is not to get to every single exercise in the homework. The goal is to say enough that you can go back and practice the homework more and correct things if you want. My goal is to take the exercises from the homework that I need to show you a new thing that will help you with the lab, and that's what we're doing. So I'm sticking with this. So don't worry if we don't get to exercise H. Okay, don't worry about that. But I am going to get to exercise G and stuff. So here we have the first derivative is that, right? So now we go to the next one. Uh, so we're still given that same function, but now we're asking the second derivative, right? In the we're asked the second derivative. So we just take the derivative of what we just got, right? So I'm not going to go through, well, I don't know, maybe you want to practice on your own right now, but we already know, we know. Well, I'll put it this way. One thing you could put in your homework, this might throw some people off. What's the second derivative? The second derivative is the derivative. Oh, hello. Is the derivative of the first derivative, right? I'm just literally writing here that I can just take the derivative of the thing we just got, which was negative a omega sine um, and so I'm just going to do the same thing again. I'm doing the chain rule in my head now. I'm doing the chain rule, which means I look at the derivative of the inner function is omega t plus 3.5. So the derivative of that is just omega again. So it's going to come out again, and the sign is going to change to a cosine. So I'll get negative a omega squared cosine omega t plus 3.5. Oops, sorry. Like this is the second. Well, I'm just okay. I'll put it on the next board. I'm going to write on the next board. I'm just copying. So if x equals a cosine omega t plus 3.5, then d2 dx like this is my final answer for number two. I'm looking at the time. We have 8 minutes. You can stop me if, and thank you. The people that told me, and I noticed the person that told me that we have a lab 3 this Thursday. For the record, that's another person that I hadn't heard from before then. So I totally appreciate that. I'm noticing that those of you, like when you can participate, you're participating. Like someone just like threw their hat in the ring for the lab. Good. Thank you. Like people just showing that they can say stuff when they can say stuff is definitely noticed. But okay, now here, I just took the derivative again. Okay. Oh, yeah, sure. Thank you for asking. Yes, got it. Direct chat person. Yes. But we get the notes later. Yeah. Um, 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 so all that happened was the omega came out again to get the second derivative. This then leads to an important question. This leads to the important question of G. But before I get that, like notice what we're really saying, if you stand back and look at this, we're saying that even though the function has a 3.5 thrown in it, the derivative is still of the inner is still just omega. Like part of why this is interesting, like you're not crazy for like focusing on it with me, is that what we're really saying is the 3.5 seems to have affected something. Like it's going along for the ride. The 3.5 is staying in the function every time I take a derivative. It's not going away. But but it is a constant. So there's no derivative of it. So even though it's not going away, it's not coming outside the parentheses as part of the chain rule. Like that's the subtlety here. The omega came outside both times, so to speak. Like we got an omega squared in the end, but the 3.5 didn't come outside. That's what we're trying to notice. In other words, I'm saying the 3.5 is also a constant. The 3.5 is also a constant, but it's not a coefficient, like in the language that you guys are saying. Like the derivative of omega t plus 3.5, if you want to be really technical about it, the derivative of omega t plus 3.5 is omega plus zero, right? Like the omega is a constant, but it's multiplying the variable. That's why you guys are correctly calling it a coefficient. It's a constant number that multiplies the variable. The 3.5 isn't multiplying the variable, so it just sort of died in the derivative, right? Now, why do I care? Because then G literally asks, I think it's G, asks, is x equals a cosine omega t plus 3.5, is it a solution to this thing that we keep seeing in this class? In other words, does it describe a simple harmonic oscillator? Like the thing that we keep seeing in this class is this is a differential equation of this form. Second time derivative equals -1 times a constant times the original function. That's the thing that whether you call that function x or z or theta, whatever it is, this class right now we're studying functions that do that. That where you take their second derivative with respect to time, you get back the original function times like an omega squared times -1. So is this doing that? Well, we just said that if x is a cosine omega t plus 3.5, we just said that d2x dt squared, I know we have like 3 minutes. We just said that d2x dt squared equals negative a omega squared cosine omega t plus 3.5. Well, multiplication. So I just looking at that, I don't know. Like, and if you're like me, like a few years ago, I would look at it and go, I have no idea. Like, I don't even understand what the question's asking really. But look at that for a second. Multiplication is commutative. I can rearrange. Like, I'm just going to rearrange the order of multiplication and say, we have 3 minutes, okay? And this would be a bad time to leave, but I'm going to say we could write that as negative omega squared a cosine omega t plus 3.5. So what? Why? Who cares? Why would we bother to say that? Because if I do that, then notice this whole piece is that, like this whole piece, a cosine omega t plus 3.5, that is what we were starting this whole problem by calling x. In other words, like I could substitute for that whole thing. If that's what x is, then that's what x is. Thus, if you use that x, a cosine omega t plus 3.5, if you take two derivatives of it, evidently you get -1 times omega squared times x. So yes, it does work. This is a big deal. This is a perfect place for us to, oh, hello. This is a perfect place. Like the answer to G is yes. And it's not obvious. We had to go through that work to realize this. What we're saying is and we've got 1 minute. Up until now, we've been saying if you've got a harmonic oscillator with that differential equation, if you want to make a prediction of where the thing is at any given moment of time, up until now, we've been saying, oh, do x equals a cosine omega t. We've been saying that's the solution. But now we're saying, you know what? Even if you stick a number, even if you stick a constant into the parentheses, which we never did before, even if you stick a number in, when you take two derivatives, apparently that number will stay in the parentheses, but it won't come out and mess with the derivatives with omega. Right? Yes, you may. I'll hang out. Yeah. So evidently, even if we stick a number into the parentheses, it doesn't change this fact that taking two derivatives of the x still spits back x times omega squared times -1. So evidently, and this number, there was nothing special about it. It's 1040. There's nothing special about 3.5. It could be any number at all. You could just call it phi. It's any constant at all. And that calculus would have worked. So evidently, you could stick a constant number in there, call it phi, that Greek letter phi, and you still have a solution to a simple harmonic oscillator. We need that revelation for next class. Like we're saying now, our solution to the harmonic oscillator is actually more general than we thought before. I think you guys have been great today. I really appreciate it. It's time. You can go. I'm hanging out for at least one person's question, but if any more, I'm here. But you guys can go. The recording's off. Hang in there with me. Thank you. Okay. I'm stopping the recording. Hang on one second. I think it's yeah. Stop the record.